So we're now going to take us one step further, and we're going to be talking about multivariable regression. We're going to take us one step further, and now we're going to go into multivariate regression. Multivariate regression is a lot like the regular regression we've been talking about, except rather than having one variable predicting another variable, we have multiple variables predicting one variable. We have multiple things that matter. Mathematically, this is what it looks like. We still have our y, our dependent variable, but now we have multiple independent variables. We still have our y, we still have our dependent variable. We still have our y-intercept. We still have our residual, this quote-unquote error term, the epsilon. Call it a residual. But now what's different is rather than just having one independent variable, we have multiple independent variables, each with their own coefficient, each with their own beta value. Note the explanatory variables now have a subscript to differentiate them from the other explanatory variables. Beta 1, x1, beta 2, x2, beta 3, x3, and I threw in the I there as well just to indicate that, of course, for each one of these variables there's going to be many observations, and they're all going to match up according to the element. To get an idea how powerful this is, let's go to my website and let's turn to, I think it's dataset 6. I want to say, yep, dataset 6. And so I'm going to show you how to do multivariable regression. I'm going to show you how to do multivariate regression. And I will take you through how to interpret it and what's going on. I'll give you the very basics of how to do it. Okay, so here's dataset 6. I'm going to hit that enable editing button. That's our friend. We do not want to work with country data, we'll work with housing data. So here's some housing data. I can't remember exactly where I got this data from, but it'll work really well for our purposes. So we have the price, how much the house sold for, the year it was built, how big the house is measured as square feet, the miles from the city center the house is, so whether this house is, in downtown or if it's, maybe in the suburbs or the exurbs, and then how many days it was on the market before it was sold. Some of these are really long days. The first observation is well over 2 years. So I'm not sure when this was taken. I want to say it was maybe in right after the housing crisis in 2008, just because these are some long days to be on the market. Some of them sold quickly. These are some long days. So let's imagine we want to predict price. We want to know what the price is. So we want to be able to predict what a house price is. Maybe we want to do this for lots of different reasons. Maybe we want to see if a house is a good deal or not. And so if we can get an estimated line, we can put the information in the estimated line and then see if that house is above or below what we would predict. We would also want to do this too if maybe we are someone who flips houses. This would be a great way to try to figure out what houses you want to take a closer look at, because if the house is being sold way below market value, way below what you would predict it to be, then that is probably a good house for a fixer-upper. Right. Well, if it's way above market value, you don't even want to see it. Well, way above what you would predict, I should say. Way above what you would predict. It's probably already in a fantastic shape. So, obviously, one of the big things that should predict price is how far away it is from the center of the city. If it's really far out in the exurbs, it should be cheaper. If it's really close to the downtown city, it should be super expensive. But there's always this question of how much it matters. And so, let's do an analysis. Data analysis, go into our regression. So I'm going to use for Y price. So we have a nice 100 observations. I'm going to use X. For the X, I'm going to use miles from city center. I'm going to make sure I hit that labels button, that labels option there. As you will see in a bit, it's super important that you do that. It's also important too that you include the labels when you highlight. And the output, I'm just going to put under G3. I don't really care. So here we can figure out how much it matters that the farther a city is, the farther a house is from the center of the city, how much its price should presumably fall. Right? We expect farther out of the city, they should get cheaper. So, and indeed, they do get cheaper, but wait, what minute? The p-value is huge. The p-value is 0.63. Now take a moment and try to remember, what does that mean? That's right. That means it's not statistically significant. It is not statistically significant. According to this analysis, how far a house is from the center of the city does not matter. Now, you could maybe come up with some reasoning as to why that is. Like maybe what really matters is not if it's near downtown or not near downtown, or how far away, but if it's near some sort of a hub of transportation. Like if a house is located near a metro stop, that's going to make a huge difference to its price. While a similar house, which is located also, the same distance away from the city center, but is nowhere near a metro stop, that'll be a lot cheaper. So maybe that's what's going on, but it still seems strange. What's going on? Here's what's going on. When we say as houses get farther away from the city, they get cheaper. That makes sense, right? If this house is located in the middle of nowhere versus, this is. So if we want to say, well, if there's two houses and one is located in the urban area and one is located in the country, then clearly the one in the urban area, it should be more expensive, right? So we're imagining, the house in the country being moved into the house in the urban area, and then we would expect that price to rise. Except there's another pattern we have to acknowledge. Because if you look at houses and homes that are near a major metropolitan area, that are near that downtown area, yes, it's true they're close to the downtown area, but there's something else that changes about them. They get smaller. In other words, it's not a matter of us moving this big house into an urban setting. It's a matter of moving this big house, it's a matter of moving this house into the urban setting. And as we move it into the urban setting, it gets smaller and smaller and smaller and smaller. Now, what would you rather have? Would you rather have a tiny house in the urban area or a big house in the country? Some people might really prefer this, some people might really prefer the other one, but it's not obvious which one would be more expensive. It's not obvious which would have a higher price. In other words, if we want to untangle, or when we're measuring miles from city center, we're really measuring two different things. We're measuring location and size. And we want to be able to untangle those two things, to pull them apart. And so in order to do that, we're going to need a control. A control is another variable that you put in as an independent variable that also matters. And it allows the analysis to pull out its effect. Control is kind of like an independent variable that matters. And including it allows you to isolate the effects of the independent variable you might actually care about. So when you think of control, you can think of controlled experiment. The idea is in a controlled experiment, if you're trying to measure the effect of, say, changing the diet, how does this affect, say, human health, or we might experiment on rats, then you would have these two rats. By the way, lab rats are genetically bred to be lab rats are bred to be as genetically similar as possible to remove any sort of randomness. So you have two basically identical rats, rather two groups of basically identical rats, and then you would give one of them this treatment, maybe this drug or this diet or whatever, and the other one holds things the same. And then because everything else is basically the same, you're allowed to tease out the effect of the treatment. That's kind of what we're doing here, except we start with this jumble of all of this data, and it has all these effects sort of built into the numbers that we can't observe directly. But what we can do is we can include all these various controls in our regression and tease out the effect of the one thing we maybe really care about. That's what you're going to be doing with the paper. You will have a bunch of things that determine a key variable, and you will establish two of those variables as your control, and then the third one as the one that you really care about. No. That's what you're going to be doing with the paper. You know, you have 3 independent variables affecting a dependent variable. You're going to pick 2 of those variables as controls, and then the third thing will be the thing that you want to say is affecting this. You know, so you can say, holding these other 2 things constant, this is what happens when we change this variable and its effect on that. So we got to do that here. Okay? Holding square footage constant, how does Miles from City Center change? And this is a really simple thing to do in Excel. So this is a really simple thing we're going to be doing. We're going to go into regression, and rather than highlighting just D, we will highlight C and D. Slow down. This means that the variables you want to include all have to be next to each other. So we call that idea of cutting and copying and insert cut cells and moving them around something we talked about last time. This is why I did that. Just as a refresher to see how we do that. If we maybe want to move this B over here, we can cut it and we can insert cut cells. And so if we wanted to run a regression with year and days on market at the same time, now they're next to each other, and now we can't. But we're not doing that. We're going to do it with square foot and Miles from City Center. Data analysis, regression, and we're just going to highlight these 2. I'm going to put it not there, we're going to put it right there. Now, let's see if we got this. So before we did not get any statistical significance at all. But here we did. Not only is Miles from City Center now statistically significant, all right, its value is less than 0.05, p-value is less than 0.05, but square feet also statistically significant. Its p-value is way less than 0.05. It's way less than 0.001. As we can see, excluding an important variable can distort the regression analysis, resulting in what we call omitted variable bias. It's when a variable that's correlated with the dependent variable and at least one independent variable is not included in the regression. Sometimes this problem is just unavoidable. And so to give you an idea, like as an example, let's imagine that we have education predicting income. And you can tell a story, education, people are more educated, they have skills, they get paid more. But maybe a third thing that we're not including is their intellect, their raw ability, or their perseverance, or their conscientiousness. These things we can't measure. And these things correlate with the ability to be well educated, and they also correlate with the ability to earn a lot of money. You know, people who are smart or conscientious or have grit tend to earn more money. People who are smart or conscientious or have grit tend to be better at school. So you can't really measure it. There's potentially a bias in any sort of those relationships with any sort of those causations. Now with that in mind, let's go back to the regression. So now we can do things like if we had, say, a 2,000 square foot house, and it was, say, maybe 2 miles from the city center, then that means its value would be that plus square foot times the square foot plus the coefficient times our miles, and we could get an estimated value of the house at $426,000. Note one thing about this, the way this is done, is that now we hold things constant. If we decide to, if we're, thinking about moving 2 miles out of the city, we know how much we'll save, a little bit, on average, a little bit less than $50,000, because that's 2 times, about 24, almost 24,000. We know that if we add, say, a room to a house that is 300 square feet, we can expect the value of that house to increase by about $71,000. Right. So it holds everything else constant. Now, obviously, there are going to be residuals in here like anything else. Those residuals can be affecting the quality of the house. So we can use that. And again, we have this like estimated value, and we can use that to get the residuals. Just like we did before with the other kind of data, the room professor data. But if we want to, we can just go nuts. There's no I don't want to say there's no limit, because there is, as we'll discuss, but we can, we have plenty of observations. We can just throw everything in. Who knows what matters? Who knows? Right? You just got to check. You see also why I insist you put in labels, because if we did not put labels in first row, then this would just be like, I can't remember what they do. They do like variable 1, variable 2, you don't really know what they are. So by making sure you include that area right there at the top, that first row where it tells you what it is, and then hit that labels button, then you get something that's a little easier to read. So this thing that always kind of amazed me is that the year built does not seem to matter. And note, things change here. Miles from city center almost becomes statistically insignificant. It's still statistically significant. It's just right on that line. Things change because as you add more variables, then other variables might pick up the work that normally one other variable was doing. That's what happened when we first ran the regression with just miles. It wasn't statistically significant because there were some observations that were pulling the value down because they were farther away, but because those houses were also smaller, they were putting also larger, they were pulling those values up. So when we were adding this variable allows us to untangle that, but sometimes too we get some spillover in other variables when we add even more. So days on the market, not statistically significant. Year built, I'm always surprised, not statistically significant. But I guess, a lot of work is done on houses. So maybe that year built actually doesn't really matter as much as we would think. Again, this says holding everything else constant, and I change only the square feet, then I only have to look at the coefficient for square feet to determine how the price will change. If you don't believe me, let's do a quick mathematical proof. It's not really a mathematical proof per se, but it does, because it won't be complete enough for that, but I can illustrate to you why it matters. We're going to have S equals square feet, M be the miles, P be the price. So the equation is price. We'll leave off the residual now. This is the basic equation. We'll leave out the residual period. We don't really need it. Now, let's imagine I'm going to add on some room to my house. It's going to increase its square footage. That means we have a square foot before and a square foot after. And the square foot after equals the square foot before plus x, where x is the additional value I'm adding on. So if we want to know how much the price changes, we're going to use A as after and B as before. So the price will change for a value of P, oh, let me put it this way. PA equals beta 0 plus beta 1 M plus beta 2 SA. The square foot after. The miles hasn't changed, beta value hasn't changed. PB equals beta 0 plus beta 1 M plus beta 2 SB. That means that we can, the change in price equals this value, beta 0 plus beta 1 M plus beta 2 SA minus this section right here. We agree this works. This is the change in price. So we're just going to abbreviate that change in price equals, I'm going to distribute that negative sign. And now you'll see this cancels with this. This cancels with this. Change in P equals beta 2 SA minus beta 2 SB, which equals beta 2 SA minus SB. And since SA equals SB plus X, since X is just simply saying a way of changing S, if all you want to do is find out how much one variable changed when you change it by a certain amount, all you have to do is take how much you changed it by, multiply it by the beta value, and that gives you how much the dependent variable changed. You don't need the other variables, the values for the other ones, they just cancel right out. The beta cancels out too, the beta 0, the intercept. All you need is the change of X. So if we add a square foot house, just multiply it by that. If we add a room, a 300 square foot room, 200 square feet times, in this case, $259, because that's how much the house price will go up, or at least how much we expect it to go up. Maybe it's an ugly room, right? Who knows? But generally speaking, that's what we can expect. Obviously super important if you're trying to figure out how much money to spend on it. All right, let's switch over to our country data. We're going to work a little bit more with preparing the data and cleaning it. I showed you a little bit of that, if you have to put everything next to each other. So let's imagine I'm curious about the murder rate. This is bad. That's going to be my dependent variable. And I'm curious how the age of first marriage and population density and median age. Where are you, median age? There you are. I'm curious how these three variables affect the murder rate. Now I can do a regression analysis, but I got this problem that age of first marriage and population density are not next to median age. So again, the way to fix this is to right click, cut, And then I could put it, I could right click here on H, I could right click here on I could right click here on J. In all cases, it's going, when I select insert, it's going to insert the column to the left. So I'll just put it here, I don't care. Insert cut columns, there we go. Now they're all next to each other. So let's do a regression analysis. So I'm going to make sure I highlight K1 all the way down, and for these, I'm going to go all the way up to the top. Make sure these match, of course, and then I want to put this in, I guess, H239. And I'm going to hit OK to see what is the effect of median age, age of first marriage, and population density all have on the murder rate. You know, because we can tell reasonable stories like younger people maybe are more likely to commit murder. We can tell at age of first marriage, maybe people are, you know, if they're married younger, maybe they get more desperate. Population density is if it's denser, then maybe it's easier to get away with murder because you can disappear into crowds. If it's more people you can stab. I always imagine stabbing for the murder. I don't know why, because most murders are shootings, but whatever. That's okay. And I get this error. Regression, linear estimate returns error. Please check input ranges again. If you get this error, it is because you have blank observations and the data. Excel is a really great program, but it has its limitations. It's not purpose-built for regression analysis. If you look at Stata, something like Stata, for example, that's purpose-built for them. So if we were to run the same analysis in Stata, it would automatically remove the observations where we don't have all the information for. But with Excel, we have to do that manually. It's really annoying, but I'm going to show you a fast way to do it. Fast-ish way to do it. So we hit OK, we're going to have to get out of here. When we run this analysis, we can't have any of these blank areas. And so take West Bank and Gaza. We have most of it. We have median age, we have age of first marriage, we have population density. But because we don't have information on the murders there, I think it's murders per 100,000, we can't include West Bank and Gaza in our regression. We don't have enough data. For population density is pretty common. Or take a look. Here we go. Take a look at Malta. Malta, we have murders. We have the murder rate, which is very low. We also have population density. We also have median age, but we do not have age of first marriage. And as long as we want to include age of first marriage into our observations, in our analysis, we can't include Malta as an observation. So some of these observations have to go. They have to be deleted or sorted out or something. We cannot use them. Now, there are two ways to do this. One is a really irritating way, is to go through and then, oh, we can't have American Samoa, right-click, delete. Oh, we can't have Andorra because we're missing these two right here, right-click, delete. And then just go through every single one of them bit by bit. Don't do that. It's incredibly time consuming. We have over 200 observations to look at. Don't do that. There's a faster way. Click this triangle button here to select all. Go to data, go to sort, and we're going to sort things by our 4 variables that we have. First, we will sort by median age. When we do that, it will take all of the observations that we can't use and put it all in one place. Now, we can delete them so we don't get confused, or if you feel bad about deleting data, you know, you don't have to worry about that. You can just sort of now only pay attention to these observations. And so we'll highlight all of those, sort, and then we'll sort
age of first marriage. And you see when we do that, now these observations are taken out. And now we only have to worry about these. And we'll do the same thing for murder rate. Oops, no, I don't want to do that yet. We'll do the same thing for population density. Looks like we are not missing anything for population density. So we will move on to, at least once we removed median age and age of first marriage. So we will then move on to murder. Okay, that looks like we don't have these. And so, but these we all have. Granted, we lose a lot of observations. We used to have, you know, something like, oh, we used to have 236. You have to say 236 and 237 because you have the data, you know, the labels in the first row. 236 observations. We now only have 168. I'm sorry, 167. That's still really good. But now we can run the analysis. So know what I did there? I just removed one of the variables, set it off to the side, removed another one, set it off to the side, so on and so forth. And then this is now what I care about. So data analysis, regression, and rather than going all the way down there, we will go to 168. 168. We'll still put it all the way at the bottom. And now we hit OK, and we got it. I want to point out that our sort function, it's an incredibly useful function for a lot of everyday things. Now, the sort option, we should say, the sort and filter under data. It's an incredibly useful thing to be able to use. I personally use it a lot for lots of different things. So it's always nice to be able to visually manipulate the data. Just really make sure that when you use that sort function, select all the data. Because if you only select one column and you sort it, then it's no longer going to be matched to its element, and the data has just become worthless. So if I were to have just sorted median age, example, then let's do murder rates from lowest to highest, and I had just sorted column K, then whatever country is listed here, I think it's Afghanistan. I think it's Afghanistan is listed here. Then that means rather than this 0.435 being the UK's murder rate, that 0.435 would be associated with Afghanistan. We don't want that. We're making a mess. The data won't mean anything. Right? So always make sure you select the whole thing when you sort, or at least you select it by rows, like I did here, to make sure that everything stays in alignment when you sort it. Otherwise, you'll get a mismatch and then you'll ruin it. You can also, if you want to, add levels to sort, as long as we're talking about it. This really isn't terribly helpful here. It's helpful when the first sort function, it's possible to get a bunch of stuff that's the same. Like if we had like a continent variable, then we would put all the countries that are in Asia all together, and then you can sort through. So within that grouping of Asia, then you would sort by murder rates. And so you can find which country has the highest or lowest murder rate within the group of Asia, which country has the highest or lowest murder rate within the group of Europe, etc., etc., etc. So that you can have lots of different levels of that, but it's not terribly helpful if you're not using categorical data. Okay, so we ran this regression. Let's take a look at the results. And you see median age is statistically significant. None of the other ones are. Their p-values are way too high. But median age is statistically significant. And it's a very, very tiny p-value. Let's talk about dummy variables. So recall that when we were discussing categorical variables before,
we ran into this issue of turning them into numbers. I said you can't really turn it into numbers, but you kind of can, and we'll talk about that later. Well, that's what we're going to talk about now. But so before, when we were saying, like, if we want to turn, a favorite color into a number, you can't just say green is 1 and blue is 2 and red is 3 and so forth, because you're assigning sort of relative values to them. Like 3 is, larger than 1, but red is not larger than green. Doesn't make sense. We don't have that problem when we talk about numeric values. Obviously $50,000 a year is bigger than $20,000 a year, and not only bigger, but more than twice as big, right? It makes sense to apply numbers there. But for categorical data, it doesn't really, not in that way. It doesn't work. But what you can do with categorical data is, what you can do with categorical data is you can turn it into a question, and you can make it a dummy variable. A dummy variable has a value of 0 or 1, with 0 being no and 1 being yes. So we could, rather than saying like male or female, or has been to jail, has not been to jail, or faces bankruptcy or does not face bankruptcy. Those are categorical variables. And what we can do is we can turn that into a question. Male, question mark, face bankruptcy, question mark, will graduate, question mark. And then we can say 0. If the answer is no, they're in the not graduate or not facing bankruptcy category. Or 1, if yes, they will graduate. They are facing bankruptcy category. So that's how we can split. That's how we can assign a number. It's an on or off switch, a 0 or a 1. If it's something like favorite color, then we can turn it into a series of dummy variables. Is your favorite color green? Question mark. Is the observation's favorite color red? Question mark. Blue? Question mark. Take, for example, this. Let's imagine we had a series of dummies. We were trying to figure out, that seems kind of mean to call them dummy variables, but they are just a 0 or a 1. There's not much to that. Let's imagine we had a series of dummy variables that we use to express where somebody lives in the DMV area, the DC, Maryland, Virginia area. There's a person here, there's a person here, there's a person here. Then we could ask the question, does this person live in DC? Question mark. Maybe they don't. 0. Do they live in Maryland? Question mark. Maybe they do not. 0. Do they live in Virginia? Question mark. And they do. Or maybe they live in DC. They do not live in these. Or maybe they live in Maryland. They do not live in these. This assumes that they only have one place of residence. That's why I pick residence. Maybe they don't live in any of these places. Perhaps maybe they live in West Virginia, which some people do. Then it's 0 for all of them. So that's how we're able to take something like a categorical variable and essentially turn it into a series of dummy variables, and thus turn it into something that we can analyze. Now, this system I essentially have 4 categories here. I have DC, I have Maryland, I have Virginia. I also have none of those. That's what this row of zeros is for at the bottom, for someone who lives way out there. I've met people who live in Pennsylvania, even though they work maybe in the suburbs of the DC area. You hear about people living in West Virginia. So it's possible. If, on the other hand, we only want to look at people who live in one of these 3 places, then this person obviously is not included, and we do not need one of these variables. we no longer need Virginia, because if there's only 3 possibilities, and this person is not in DC and they're not in Maryland, then they have to be in Virginia. So when all categories are mutually exclusive and completely exhaustive. Hold on, my cat's playing with something.
What are you doing? Are you playing with something? What's the attention? Come here.
My cat. Yes. So when all the categories are mutually exclusive and completely exhaustive, then the number of variables that you need in order to express this categorical variable, the number of dummy variables you need, let's make that clear, the number of dummy variables that you need is equal to the number of categories minus 1. Let's talk a little bit about what we mean by mutually. Well, do you want down? Okay. When we say mutually exclusive, we means if you're in one category, you cannot be in the others. A person cannot live in 2 different places at the same time. At least we know we're assuming a primary domicile. Completely exhaustive means we've covered all possibilities. So when we had the DMV and it was DC, Maryland, and Virginia, and then I said, but there could be like a 4th place because they could be way out there in a different state entirely, then that wasn't covering all the possibilities, just those 3. But then when we switched to saying only those people who live in one of those 3, well, by definition, that is all the possibilities. And since you couldn't live in 2 different places, then we only needed 2 dummy variables, not 1. Then we only needed 2 dummy variables, not 3. Let's take a moment and appreciate why we need both of these requirements in order to get number of categories equal to minus 1. Number of dummy variables equal to number of categories minus 1. If it's not mutually exclusive, if you could be in 2 different categories at the same time, like if it's say what you're majoring in, then just because someone is in one category doesn't mean that any excluded category they're also not in. No, so whatever we take out, well, they could be both a music and math major. I don't know. So you have to have them all then. If all categories aren't completely exhaustive, then if we remove one on top of that, then and someone is in neither of the ones we have left over, then we don't know, are they in the one that we didn't include initially, or are they in the one that we took out? We don't really know. So you need both of these requirements in order to be able to remove one of the options, essentially. If we were to do the number of colors, well then, since you can only have one favorite, and since if you have one favorite color, then that means you only can have one favorite. And since there's only a certain number of colors that people can see, so there is like, we can consider all the colors, then we would need the number of colors minus 1 for that series of dummy variables. Of course, there are probably hundreds of thousands of colors, if we consider all the different shades. That's a lot of dummy variables. I don't really know anyone's going to say eggshell white is their favorite color. But I mean, we kind of have to include it, right? Because if someone says no to all the ones we have include, then we don't know what their favorite color is if there's more than one excluded dummy variable. So it would be hard. One way to do that, though, is to just only include the variables only include the colors where someone says, yes, that is my favorite color. That's one way to fix it. And then there are no rows of zeros, so there's no mystery.
Okay. So let's see what this means for purposes of working with Excel. Let's go to our regression. So I want to run a regression analysis. This is our rate by professor data again. We have quality. I want to predict quality. I want to predict it with difficulty, but I also now want to include the dummy variable hot. So this is what this was here, right? You can see this professor is considered hot, has a 1. This professor is considered not hot, has a 0. No, answer question. Let's do a regression analysis. Regression. We are quality. What are you doing here? With these two. Make sure they align. So here's our regression analysis. Both difficulty and hot are statistically significant. Right? Both of those values are, both those p-values are less than any alpha we would use. Less than 0.05 certainly, but less than 0.01 and 0.001. Note, as usual, this coefficient is slightly different, right? This is slightly different than before. We don't get that. This is slightly different than before. Right, rather than negative 0.86, it's negative 0.75. Because again, some of the hot variable is taken out, is moving away as some of the, doing some of the work, I should say. Interpreting this, though, is simple enough. A professor is either hot or not hot. There are no degrees because it's a dummy variable. So that means that the largest it can be, like if, for example, a professor decides to want to increase their ratings and they know that hotness matters, it is statistically significant. Maybe they go to the gym and they maybe get some plastic surgery, and they do something to themselves that makes them hot. And according to this category, that makes them more attractive. The most it can ever increase, according to this analysis, then, is 0.55, right? Because you are either hot or not. This is either a 0 or a 1. If the hot is a 0, then you take 0 times 0.55, and nothing is added to your final result. If you are hot, then you take 1 times 0.55, and 0.55 is added to the final result. It's added to the quality. Being hot adds 0.55. If on the other hand that you decide to let yourself go and get kind of fat, and and whatever reason students don't consider the professor hot anymore, then losing that will mean that they will give you then that means that your coefficient will only fall by 0.55, right? Going from a 1 to a 0. Can't fall any more than that. As a side note, too, it's always important to tell a story for why hotness should matter, and in and of itself. And maybe hotness matters for one. Maybe students just like attractive people, right? People tend to like more attractive people, and they give them better ratings. It could also be that maybe more attractive professors are easier to pay attention to. There is, of course, a problem with this, is that a lot of international students don't know what the hot means. I mean, it doesn't matter anymore because they removed it, thankfully. My Raber professor has removed that option to judge professors by their appearance. But back in the day, I would do this lecture with international students, and they had no idea what hot meant. They thought hot meant, is the professor's class hard to get into? It's not hot as in attractive, but hot as in popular. And that creates this interesting thing of it's not a hotness causing quality, it's quality causing hot. Because again, people are tagged as hot based on student ratings. And if a lot of these international students thought they were just judging a professor based on how hard it is to get in their class, quality caused hot. So it's not a perfect analysis, but it is illustrative of this idea and the limits of dummy variables. Because difficulty can increase or decrease, by a lot, by many points. But hot can only be a 0 or 1 for any observation. Right? For any one observation, hot can either be a 0 or 1. By definition, it's a dummy. If we wanted to predict a dummy variable, if we wanted to put a dummy variable in the y area, then predicted values are a different story. We'll talk about that later. But on the independent side, dummy variables are either 0 or 1, and that limits their influence on the result. Of course, it does depend on the coefficient. Now, you'll note that there's a lot of other stuff going on here. We have observations, which we know, but there's we have this r squared and adjusted r squared. We've talked about this. This is the residual sum of squares. This is the explained sum of squares. We don't know what this is. F and significance F. And we will talk about that next class. See you then.